Hello everyone and welcome to the lecture for nanomedicine on size and charge and other properties that matter in nanoparticles. So we had talked a lot about size and that in general the size of the particle will dictate the blood half-life and a lot of the accumulation. But there are other things to consider, and this is really well illustrated in this paper by Louis Balagh and Mohammed Khan. It's in Nanomedicine 2007. But they systematically went through and looked at the charge and size of different gold nanocomposite particles. So we can use this as a starting point to see how size and charge change things. So first let's talk about how we actually look at distribution or biodistribution. So in animals what we do is we will inject the animals with the agent and then at different time points sacrifice them, take out different tissues and determine how much of that agent that we injected is in the different tissues. And we plot this by percent injected dose per gram. So these percentages, because it's percent injected dose per gram, we've corrected for concentration. It's basically a concentration. They don't have to add up to 100%. That's one of the things that's kind of confusing. So this is how we typically do this and graph it. So these are the times. So 5 minutes, 1 hour, 1 day, or 4 days. So here's the blood. These are 5 nanometer gold nanoparticles that are positively charged. And so what you see is over time, here's our PK, and you guys have seen this as a list of time versus concentration or percent injected dose per gram. And from this, you guys know that you should be able to calculate the blood half-life. Here's what this looks like in the brain, so really no difference. The muscle just decreases, and there wasn't very much in the muscle to begin with. The pancreas just decreases, so at 5 nanometers, they can go out of the bloodstream. So this is how much accumulates there, but you can see it go into the pancreas and then back out. These animals had a tumor, so here they are, 5% injected dose per gram, 1 hour in 1 day, and then they start to go by 4 days. Here's the heart, and the heart is really going to mirror the blood because the heart has a lot of blood in it. The kidneys, this is the filtering organ, and so the kidneys are a proxy for the urine. Here's the lungs. The liver, because these particles are small and positively charged, there's not really going to be much in the RES organ, so liver and spleen. And then we can also look at where this is getting excreted. So these are the kidneys. This gray bar is the kidneys. And this is this is the urine, actually. This is feces, and then this is mixed. So sometimes we can't separate it too well. But for this size particle, the majority of it is present or being excreted through the urine. Exactly what we would think based on the size of this particle. So now let's see what happens if we make this particle negatively charged. And so look at the contrast in the blood half-life. Most of it is cleared by 1 hour. That is in sharp contrast to the positively charged, even though this is 5 nanometers, and this is because this is going to rapidly be opsonized. And how do we know this? If you look at the liver and the spleen. So before, because of its size, it was being excreted through the kidneys and the urine. This time, because as soon as it gets in the bloodstream, it's highly negatively charged. Proteins are going to surround it, and then it's going to be seen as bigger, and it'll be directed towards the RES for opsonization and delivered to the liver and the spleen. So this is a negatively charged particle, and no matter the size, so you really shifted the biodistribution away from the kidneys and to the liver and spleen. And now also look at the tumor, because so much of it so quickly is going to the liver and spleen, there's less available for it to go in the tumor. And this is all due to EPR effect. This isn't even targeting. So if you want to go into a tumor, you do not want to have a highly negatively charged particle. Now let's look at an 11 nanometer negatively charged particle versus the 5 nanometer negatively charged particle. And what I want you to see is look again at the blood. This is percent injected dose per gram. Between 5 minutes and 1 hour, the 11 nanometer particle is almost all out of the blood. It's not really, it's even less in the tumor. It's staying in the heart. Here's the kidneys, lung, and then the liver and spleen. There's so much in there. It's 200% injected dose per gram in the spleen, just by increasing the size. And now compare that to the 5 nanometer where it was 25% injected dose per gram in the liver. So the combination of size and charge means that you're really putting this in the liver and the spleen, and a little bit more in the lungs, so 10% versus 5%, so twice in the lungs, and a lot more in the heart. And I'm not exactly sure why that is. Maybe it's so big it's aggregating and getting clogged in the heart, but that's a lot in the heart. So here is a 5 nanometer positively charged gold nanoparticle. Here's the elimination in the urine and the feces. And then this is the 11 nanometer negatively charged particle. So again, compare and contrast. Here it is in mostly in the urine with a little in the feces. It's almost 50%, 50-50 in the kidney, in the urine and the feces. And again, that's because it's going more towards the liver and the spleen, where it can be broken up into smaller pieces, which then can be filtered through the kidneys and put into the urine, or put into the gut where it's incorporated in the feces. So a lot of it. But if you look at the percent injected dose per gram, most of this, 36% at these hours, so quite a bit of it, is leaving through the urine, where here it's only 2%, and that's because it takes the liver a little bit longer to digest the particle. Here's a 22 nanometer particle comparing and contrasting versus positively charged 5 nanometer. So again, in the 5 nanometer, mostly in the kidneys, where here in the 22 nanometer, most of it is again shifted to the spleen, liver, and some of the lungs, just because the particles start to get bigger and they start to aggregate, and so they'll get stuck in the capillaries in the lungs. But again, this is comparing and contrasting the biodistribution. Here's the 22 nanometer, so it doesn't really stay in the blood that well. It goes mostly, almost immediately to the spleen and the lungs and the liver. And then finally, here's an example of the PVPK model. Here's a generic one, long adipose, so you guys should be familiar with this. And then here's the pharmacokinetic curves of the negative 5 nanometer gold things that we just saw. So here is all of the different, the liver, the lung, the blood. These are what all of these curves look like. And so what you're trying to do is you're looking for the ratio of a tumor to the blood kind of ratio. So you want the time point, that's when you do the imaging, or that's when you do the multiple dosing to keep it in the therapeutic window at these different time points. So that's all. That's a very mini lecture on the size and charge and other properties.